Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. As you know, within this module we are trying to understand that how does the operating system manage the CPU by providing this abstraction of a process. And within the second module we are currently on the fourth topic, that is process system call API. So now we are nearing the end of this topic. We have covered all the system calls that we wanted to, right? So in this video we are going to summarize all that we learned, right? So at a very high level, the idea behind this topic was to understand the system call interface of the Unix operating system, to be specific, and we wanted to understand those system calls which allow us to perform useful operations on the processes, right? This whole discussion is around processes, and in this topic we wanted to look at the system calls which allows us to perform useful operations on process. And we looked at 5 to 6 system calls, right? Four were the major basic system calls, like the fork system call that was for process creation, exec also for like running a new program. The fork and exec are related to process creation. Then we looked at the exit system call for process termination. After that, we talked about the wait system call, which helps one process to wait on another. Then in the previous video, we talked about how the Unix shell is constructed, can be constructed using the four basic system calls. We also looked at two miscellaneous system calls, that is get PID, that returns the process ID of a process, and finally we looked at the kill system call that is used for signaling, right? So this was a brief overview of what all we covered. So in this video, I'll quickly go over the each of the videos that we went through and recall what we studied in this topic. So the first video in this topic was about laying out a basic introduction, right? The process system call API, right? So the system call API is the interface that the operating system exposes to the layers of software above, and we wanted to look specifically at the process system call API, right? So I laid out a basic introduction, like we talked about the compute stack and how the operating system, basically at the very bottom we have the hardware interface, how the operating system simplifies this hardware interface by providing a layer that is made up of abstractions, right? And to use these abstractions we need system calls. So basically, since these are abstractions which are there to simplify the hardware interface is provided by the operating system, any operations on these abstractions has to be provided by the operating system. So since process is an abstraction, so operations on processes like creating a process, terminating a process, right? All of these have to be provided by the operating system. The way the operating system does this is via the system call interface, right? For every operation that you would want to perform on these abstractions, the operating system exposes a system call. So the interface of the operating system from the perspective of the user application is that of a bunch of system calls. It looks like a library of system calls, right? Then we laid out the different process operations that we would cover: process creation, termination, waiting, and some miscellaneous operations, right? So these are the system calls that we studied in this topic, right? So next we talked about the fork system call. We laid out a basic introduction. In the second video we talked about the API. So the fork system call is simple. Its API is simple. It does not take any argument, and it creates a new process by duplicating the calling process. And what does it return? It returns the process ID, and this star indicates that the return, basically there is a special condition. So the fork system call returns twice, once in the parent and once in the child. In the child, the value returned by fork is 0. In the parent, it returns the process ID of the child process, right? So this is how the overall like flow of fork looks like. Let's say we have a process A, it invokes the fork system call, then the control goes to the system call routine in the operating system, and when we are done with it, basically what we have is a new process, right? This process is different from this in the sense we have a new distinct process, but the code that is being executed is the same as the one of the parent. So process B is a duplicate of process A, and right, and fork system call returns twice, once in the parent and once in the child. So this is how we create a new process using the fork system call. It creates a copy, right? And then in the third video we took a closer look at the fork system call. We saw that the, like in the previous video, right, in the second video when we introduced fork, we said that fork system call makes a copy of the original process. But we looked in more detail in this third video and said that the child process is not an exact copy of the parent process. There are some minute differences, and we talked about those differences. First of all, the return value is different. In the parent process, the return value is the process ID of the child. In the child process, the value returned is 0. And this return difference in return value is very useful because this helps us to determine in which process we are currently executing, whether the parent or the child. We also saw some other minute differences, like the process ID and the parent process ID of the parent and the child are different, right? So we talked about the fact that the parent is not, so the child process is not an exact copy of the parent. Some fields like the process ID, the parent process ID, all of these are unique to each process, right? So that is what we covered in the third video. And finally, we also talked about the fact that since processes create new processes, right, and these new processes will create their own children by calling for, eventually in the system what we have is a process tree. At the root we have one initial process, the special process that is started by the operating system. Its name is systemd in Unix, right? And this initial process then forks and creates new processes, right? And eventually what we have in the system is a tree of processes, right? So after fork system call, we looked at the exec system call, right? So the exec system call, as we studied, allows us to run a different program. While the fork system call allows us to run a new process, the exec system call runs the same process with a new program. And how does it do that? It basically, so this is one of the versions of the exec system call, the most simple one, right? What it does is that it takes the name of the binary file that has to be executed along with a list of arguments that have to be passed to the new program. So it loads up this file and executes this binary file with these arguments. And it does not return when it is successful. Only when there is an error, it returns the code of -1. So since the previous program, since the old program is replaced with a new one, there is no place to return to. That is why when there is a successful execution of the exec system call, it does not return, right? And this is the flow that we saw. So basically there is a process A and it executes the exec system call. It passes the file name along with the list of arguments that have to be passed to the binary file. What does the exec system call do? It locates this binary file. It is a binary file that can be executed, right? This is lying on the disk. It loads up this file and uses this file to replace the memory image of the original process. All of the different sections are replaced, and what we have is a new program, right? The same process. We do not create a new process like we did in fork. We run the same process, but what we do, we run a different program from the original one, right? So this basically summarizes what we do in exec system call. This is the process, this is the process control block, and this is the process address space. So this is basically the memory image of the process. When we call exec, the old process's memory image is replaced with that of the new program. So basically this is the program, that is the binary program lying on the disk. This is used to replace the memory image. The code is replaced, the data is replaced, the heap is reinitialized, the stack is also reinitialized with the new arguments. We have the same process, but all of the program is replaced with a new one. So fork allows us to create a new process, exec allows us to run a new program, right? And in the next video, we talked about the differences between fork and exec in more detail, right? So this table summarizes what all we discussed. At a very high level, the most basic difference is that fork creates a new process, whereas exec runs the same one. Fork runs the same program. It is basically a duplicate of the parent process. So the code that is being executed is the same, whereas exec runs a new program. So fork is new process, same program. Exec is same process. Sorry, fork is new process, same program. Yes, and exec is same process, new program, right? So fork returns twice, once in parent and once in the child. Exec does not return in successful execution and starting of execution. So fork starts execution right after returning from fork, right? So basically, when there is a fork statement in the child process, execution will not start from main. It will start from the point after the uh, fork statement. Whereas in exec, the execution starts from main. So these are some of the basic differences, important differences that we discussed in that video. We also discussed how fork and exec can be used together. They're meant to be used together, right? The fork allows us to create new processes but runs the same program. So the problem with using fork alone is that although you will have new processes in the system, but they will be running the same program, but we do not want to run the same program always, right? Whereas the case of exec is that you'll have the same process, and but you will be running a different program. Again, this is not also very helpful because we are now constrained to using the same process. So we combine both of this. We call fork, we create a new process, and then we call exec in that, so that now we have two different processes running two different programs. So fork and exec are meant to be used together, right? We also discussed why there is such a design where fork and exec are separate, why process creation requires two system calls in Unix, right? So the reason is that this separation of system calls, that is creation of a new process and launching of a different program, fork and exec, this separation allows for several useful features in the Unix shell, like output redirection and the concept of pipes. Basically, just before calling exec, you can alter the environment of the new that of the child process. You can redirect the standard output or standard error to a file, that is output redirection. You can connect the output of the new child with that. Basically, you can connect the output of the child to a input of another process. So in that way, you can chain different processes using pipes. So all of these useful features, as we discussed in that video, are it's crucial that we have separate fork and exec to enable these useful features in the Unix shell, right? So that was about fork and exit. In the sixth video, we talked about exit, the system call that exists for process termination, right? We discussed the different scenarios in which processes exit. There can be voluntary exit, there can be involuntary exit. Involuntary exit, basically the process is initiating the termination on its own. It could be due to a normal completion, or after discovering or after encountering an error. The point is, in voluntary termination, the process is initiating the termination on its own. There could be also cases when the process is exiting involuntary. It is like forcefully, it is basically due to some external reason. Examples include exceptions. If the process does something illegal, then the operating system will forcefully terminate the process, right? Here, the process does not have any control. It is being forcefully terminated by some other process, right? Another is being killed by a signal, right? A process can also get killed by another process due to a signal. So these are examples where the process is terminating, but it is not voluntary, right? So these are all the scenarios we discussed where process termination occurs. The reasons in also we discussed. Then this is the interface we talked about. It has a very simple interface. All it takes is a single integer, that is the status, the exit status, that has to be returned to the parent. And this exit status is an integer which is signifying the reason of exit. If it is 0, by convention, it denotes that the execution of the process was successful, whereas if it is a non-zero integer, then it denotes that there is an error. So this exit status is used to communicate the overall result, in the sense the status of execution, to the parent. And when there is a, okay, so exit system call does not return whether successful, whether failure. It does not return. After exit, the whole process that had called exit is terminated. All of its resources are deallocated. As you can see, this is process A, and when it invokes this exit system call, it passes the exit code. And once this is done, this whole process will be terminated. All of its resources are deallocated except for the process control block. The process control block is not deallocated because it stores the exit status, right? So this exit status is stored so that when the parent calls wait, it can collect that exit status from the process control block. And once that is also collected, this PCB is freed up, right? So this is important because even if the process terminates, we want that its exit status should be propagated to the parent, because the parent created a child process and it needs the information to take further decision. Like if a child is successful, then it might need to take some action. If the child has failed, then it might do another thing. So this exit status is a very crucial piece of information that needs to be propagated to the parent even after the process has terminated, right? Then in the next video, we looked at the wait system call. So wait system call is used by one process to wait on another process, right? It's basically used by the parent to wait on their children process. So what does wait do? It suspends the execution of the calling process until one of its children terminates, right? A process can launch many, you can say many child processes, and that parent often wants to wait for its children to complete. So there it can use the wait system call. When the parent calls wait, its execution is suspended, it is put to sleep. until one of its child terminates, right? So this is the interface of the wait system call. What arguments does it take? It takes an integer pointer. If it is, it can be null also, right? As you can see, if it is null, then we don't do anything. If it is not null, then this integer pointer is used to store the exit status of the child that has terminated. And what is the return value? It returns the process ID of the terminated child, right? And this is the overall flow of what happens when we have the wait system call. We have a process, it calls fork system call. So it creates a child process. So now we have a parent, that is process A, and a child, that is process B. Then let's say the parent goes first and calls wait. When it does that, it gets suspended, right? It now waits until its child terminates. So process B can continue its execution, call the exec system call, and eventually when it terminates, then only process A will get unblocked, then only it will resume its execution. The point is, process A has to wait until process B, that is one of its child, terminates. That is how the wait system call is used. If it so happens that the child terminates before the parent has called wait, then in that case there is no need to suspend the execution. The parent process returns immediately, right? This is the case when the child process was created and it went on, executed, and it finishes before the parent. So when the parent calls wait, it returns immediately. So these are the two cases: either the parent can call wait before child exits, or the child can exit before the parents calls wait, right? And finally, the important part is that collecting the exit code of the child. So when a child terminates, as we discussed, all of its resources are deallocated except for the process control block. There, the information associated with the child is kept, and the important information is the exit code. So if the argument to the wait system call, that integer pointer, is not null, then the exit code is stored in that status variable, the status pointer, right? So that the parent can then this is used to propagate the exit code to the parent. The parent can inspect the exit code and then take some appropriate action. The process ID is also returned to the parent for the child that has terminated. So this was about the wait system call. And then there is the important concept that we discussed, that is of zombie processes and orphan processes. So what is a zombie process? A child that has terminated but has not been waited for becomes a zombie process, right? For example, let's say we have a process A and it creates some children processes. These are the process control blocks of these children processes. Let's say what happens now is that, let's say these processes terminate, but process A, the parent process, has not called wait. When children processes terminate, right, and the parent has not called wait on them, then they become zombie processes. In zombie processes, there is no process in the system. All of the resources have been deallocated, but the kernel maintains a minimal amount of information about these children processes in the process control blocks. So all we have is the process control blocks for these zombie processes. They are almost dead, but not exactly. So the process control blocks is kept because it has the exit code, and when the parent process calls wait, all of these exit codes are collected and the process control blocks for the zombie processes are cleared, right? And then we discussed about the orphan process. What is an orphan process? A process that continues to run after its parent process has finished, right? That is called an orphan process. In the zombie process, the parent has not called it and the child terminates. In the orphan process, the parent terminates before the child, right? So let's say again we have the same example. We have a process A, and let's say it has multiple children. In this case, instead of the children terminating here, let's say the parent terminates. In that case, these processes are now without a parent. That is why they are called orphan process. And in this case, what happens is that they are adopted by the init process. So now init process, the root process, is the new parent of these processes. And the good thing is that when these processes will terminate, they basically they'll become zombie processes, and init process can take the responsibility of calling wait on these system calls and clearing up these zombie processes, right? Once the orphan processes die, they eventually become zombie, and someone needs to be there to clear those zombie processes. That is why we have the init process, right? So this was about zombie and orphan processes. And in the previous video, we took all of the system calls we discussed, that is fork, exec, exit, and wait, and discussed how the Unix shell works. So this diagram shows how the Unix shell works. So basically the shell, it takes commands as input from the user, and it creates a new, basically it calls fork and it creates a copy of the shell process. So let's say this is the parent and this is the child, and Then it goes to wait. The parent shell process calls wait, and it suspends its execution. And the child shell process then calls exec to execute the command that has been given by the user. So now the program of the shell is replaced by the command that has to be executed. And in between fork and exec, the shell can also alter the environment of the new, uh, basically of the new process that is being executed. So when I say alter the environment, it could be like, as we discussed, output redirection or pipes, right? All of these features can be enabled. So this is how the shell can alter the environment of the new process. And once that is done, once the process is finished, it can call exit. And once it does that, the parent shell process resumes execution. So this is the cycle that is followed again and again. The parent process, the shell process creates, calls fork, creates a child process. The original parent process goes to wait. The child process calls exec and executes the new command. And when it exits, the shell resumes execution. So this is how the shell continues on and on, accepts user's command, executes that, and this is how it iteratively uh, works. So the idea was that to understand how we can use all of the system calls that we discussed and make a Unix shell out of it, right? Then we discussed the timeline diagram for the same, right? This describes the same, but in a timeline fashion. You can see the shell calls fork, creates a copy of the shell, which eventually goes on and waits. Here we have a context switch, and then here we switch to the child process that is created by the shell. So the child process calls exec to execute the command that has been given by the user. Here I have shown the main function also, because the startup function is the one that passes the arguments to the child process. And once the main finishes, in the startup function we have the call to exit. So this diagram kind of shows all of the things that happen, all the four major system calls, also how the main function works, right? And finally the child process exits, and then we go back to the shell process, because the wait now returns. Once the child shell process exits, it the parent shell process which was waiting, that also resumes execution, so that it can accept a new command. So this is a timeline diagram of what happens in the life cycle of a shell, right? And when we discussed two miscellaneous system calls, one is the get PID, which returns the process ID of the calling process. And then we also saw the kill system call, which is used by one process to send signals to another process. It takes the process ID to which the signal has to be sent, and the integer denoting which signal has to be sent, right? And we saw an example where we took where we used three different signals: one to pause the process, another to resume the process, and one to terminate the process. So we understood the working of the kill system call using this example, right? So guys, this was it for this video. Now we have completed topic 4, process system call API. We're done with this topic. In this topic, we discussed all of the major system calls that allow us to perform crucial operations on processes: process creation, termination, waiting. We also discussed some miscellaneous system calls that allows like sending signals to different processes. So this was a discussion about the Unix system call interface and the useful system calls that are there, which you can use to uh, perform operations on processes, right? From the next video onwards, we will start a new topic that is about the time sharing. Now we have a good understanding of processes. We have spent 4 topics on understanding processes, right? In the first topic, we discussed process introduction, right? There we laid out the basics of processes. Then in the second topic, we talked about the process address space, the view of the memory that a process has. Then in the third topic, we discussed about system calls, exceptions, and interrupts. Basically, these are the different events that happen in the life cycle of a process, which help it to communicate with the kernel. We saw the interaction of the process with the kernel using these events. And finally, here in this video, in this topic, we focused on the system calls and we saw the process system call interface. So now there is a good understanding about the process. Next 2 topics would be about understanding how we can run different processes on limited number of CPUs. Now we will look at how the processes are juggled on the CPU, right? We will talk about the mechanism in the next topic, that is time sharing, which we will talk about the details of how limited number of CPUs are shared between the different processes that allows us to run more number of processes than the number of CPUs. And finally, in the last topic, we will discuss about the different CPU scheduling algorithms that allows us to take decision as to like which process should get the CPU. So these two topics, the next two topics would be kind of related, and they would be around how multiple processes share the CPU. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.